Hello guys, welcome to new video of M.Sc Mathematics. So in the previous video, what we learned what is a binary operation, what is binary structure, and what is group. So I am just recapping these things so that if you have not watched the previous video, then you can understand whatever I am going to impart training in this video. The things on which I will be going to impart you the training, you will understand. That is why, so that you can understand, that is why I'm going through or recapping the things what we have learned in the previous video. So in the previous video we have learned what is binary operation. So what is binary operation? A binary operation is an operation on two elements of a set to produce another element in the same set. In other words, a binary operation is closed over the set of elements used by the operation. What does that mean? I have given you the example. Let us suppose we have set of real numbers, okay, and consider addition as an operation. Okay, consider addition as an operation. So if we add two real numbers, what we will get? We will get a real number. If we subtract a real number from a real number, what we will get? We will get a real number, right? If we multiply a real number by a real number, what we will get? We will get real number. But if we divide any real number by 0, then what we will get? Undefined, correct? So if you consider the operations addition, multiplication, and subtraction, and consider the set of real numbers, you can see that multiplication, addition, and subtraction producing the real numbers, okay, producing the real numbers. But division, if we consider uh, 0, if we consider that we are dividing any element by 0, okay, then it will always produce undefined, okay. So for multiplication, subtraction, and addition, we are always getting a real number. But for division, we are getting undefined when any real number is divided by 0, correct? So undefined is not belonging to the set of real numbers, not belongs to the set of real numbers. So you know that undefined does not belong to the set of real numbers. So here we can say that the operation division is not closed. Division is not closed over the set of elements of real numbers, correct? But addition, subtraction, and multiplication are closed over the set of elements of real numbers. So here, if we consider the set of real numbers, a binary operation, what will be the binary operations? Binary operations will be the addition, subtraction, and multiplication, not the division, correct? Not the division. So that is why we define the binary operation. If you have not gone through my previous video, then please take a screenshot of this, because in all of my videos I always told you to take screenshot of this, because if you uh, pin up this in sequence, okay, if you just take the screenshot and pin up the screenshot in the sequence, take a printout of the pinout, take a printout of the screenshot and pin up those in sequence, we will have a very good notes, okay. So you understood what is binary operation. Now what is binary structure? And this is the explanation, that what I have told you, all the explanation is written here, so you can take a screenshot of this, okay. So what is binary structure? A binary structure combines a binary operation and a set, okay. The notation for a binary structure is a set of the set of parentheses where the first symbol identifies the set and the second symbol identifies the operation. So for set of real numbers, we can write like this: r binary r comma asterisk, asterisk is the binary operation, and what what can be the asterisk? The asterisk can be addition, subtraction, or multiplication, but never be division, correct? So value of asterisk can be addition, multiplication, or subtraction. So this is binary operation. Now what was group? A group is basically a binary structure, okay. The group is basically a binary structure which follows four basic properties. If a binary structure follows four basic properties. Some four properties. These are the four properties. If and only if a binary structure, if and only if and only if a binary structure follows these four properties, then we say that binary structure is a group. Okay, so what are the four properties? One is closure. What does that mean? That means if a set if we consider G as a set, okay, and if we consider A, B, C are the elements of this set, okay, and star be a binary operation, okay, then if AB belongs to G, then A binary operation B always belongs to G. That is called closure, okay. If ABC belongs to G, then A binary operation B binary operation C will be equal to A binary operation B binary operation C, okay. This is called associative law, okay. The third one is the existence of identity. So what is identity? Identity is like that if any element is if we do binary operation of element of the set within with the identity element, that will produce the same element, so if E be the identity, and A be a member, okay, then that if we do a binary operation, if we do it from left hand side, or if we do it from right hand side, it will always produce the same element, okay. It will always produce the same element. And what is inverse? Inverse is like, let us suppose we have the element A, okay, and its inverse will be defined as A inverse if A binary operation A inverse always produce the identity element, that if A binary operation A inverse always produce the identity element, okay. And for that I have given you a very simple example, that let us consider say set G having elements 0, 1 and -1, and let us consider addition as binary operation, and let's check whether the set G with having numbers 0, 1 and -1 with addition as binary operation forms a group or not. So for that how we will proceed? We will proceed like this. We will proceed like that. First we will add 0 plus 1 and check what will be produced. If we add 0 plus 1, it will produce 1, and 1 belongs to G, correct? 1 belongs to G. Then we will add 0 with -1. What we will get? -1, correct? That also belongs to G. Then we will add 1 and -1. What we will get? 0. That also belongs to G, correct? So we can say, if we do whatever operation we are doing with the elements, whatever operation, we are considering addition as binary operation, okay. So the operation we are doing, like A plus B, okay, A plus B, and here A plus B, we are getting whatever result we are getting, okay, that also belongs to the set of G, right? Because AB is element of G. Then we can say that if we write like that, A, B and C, okay. So A, B and C. Now what we are doing? 0 plus 1. That means A plus B. That is producing 1, right? That belongs to set G. Then we are adding 0 plus -1, that is C. A plus C. Again we are getting -1, that also belongs to G. Again we are adding 1 plus -1, that is means B, B plus C, and we are getting 0, that also belongs to G, right? So we can say that the closure axiom is satisfied, because what we see, what was the definition of the closure axiom? Closure axiom says that if you do the binary operation of any two elements of this set, that the result produced will also belongs to this set. And we can see that the operations we are doing with the elements of this set are the result produced also belongs to the same set, right? So you can say here that the the set is closed, the set is closed under the binary operation addition, correct? The binary structure is closed under the binary operation addition. Now we will check associative law. So associative law, what we will do? First we are doing 0 plus 1 plus minus 1, correct? What we will get? 0. Then we are doing 0 plus 1 plus minus 1. What we will get? 0, correct? So we can say that 0 plus 1 plus minus 1 equal to 0 plus 1 plus minus 1. That is associative. In the definition of associative law, what we saw? We saw A binary operation B binary operation C will be equal to A by binary operation B binary operation C, and that is happening here. So you can say this is associative. Now we will find the identity, find the existence of the identity. So we can see here that if we add 0 with 1, what we will get? 1. If we add 0 with minus 1, what we will get? Minus 1. So here 0 will be identity, because if we add any element with 0, what we will get? We will get the same element. So we can say here, we can say that for this set with binary operation addition, 0 is the identity. Okay, now we will check for inverse. So if you can see, if we add 1 and minus 1, what we will get? 0. That is the identity element. So we can say that the inverse of 1 is minus 1, or we can say the element have the elements have the inverse. So this, the element of the set has the in this set, whatever element we have, for that inverse also exists. Okay, and inverse is unique. Okay, you just keep in mind, inverse is unique, and right inverse, left inverse is unique, identity element is unique, left identity element and right identity element is unique. We will learn in deep when we learn the properties of set, properties of group. So just keep in mind for the time being. Okay, so that is how we just check whether a set with a particular binary operation is forms a group or not. Next, so this is the new thing we are learning in the previous, whatever I described before, we have already learned those in the previous video. So whoever not watched the previous video, for those guys, I have just recapped the things. Now we will check the same. We will learn the new things. So one is abelian group. So what is abelian group? If set G satisfies the following condition along with the 4 axioms to be a set. So we have already seen what are the 4 axioms to be a set, to be a group for a set with a binary operation. Correct. We already seen that what are the 4 axioms to be a group for a set with a binary operation. So now for abelian group, there is an additional criteria. What is the additional criteria? If A binary operation B equals to B binary operation A. Okay, so let's consider the set G 0 minus 1 having numbers 0, 1 and minus 1. We have already checked the set 0, 1 and minus 1 with addition as binary operation forms the group. So now we will check whether the same set G having elements 0, 1 and minus 1 with addition as binary operation forms an abelian group or not. Okay, so how we will check that? We will first add 0 plus 1 and then 1 plus 0, that is A operation B binary operation B and B binary operation A. What we will get? 1. Again 0 plus minus 1 and minus 1 plus 0. What we will get? Minus 1. Correct. Then 1 plus minus 1, minus 1 and plus minus 1, and we will get 0. Right. So we can see here that A binary operation B equal to B binary operations A for the set G having elements 0, 1 and minus 1 with addition as binary operations. So the set G having elements 0, 1 and minus 1 with addition as binary operation not only forms a group but also forms a abelian group. Okay, so what is semi-group? Let G be a non-empty set and asterisk be a binary operation on G. Then this set G together with the binary operation asterisk denoted by G asterisk is called a semi-group if and only if the following conditions are satisfied. There are two conditions condition to be semi-group. What are the two conditions? The first condition is closure, and then second condition is associative law. Okay. Now, let us consider a set. Okay, set of integers. Let us consider a set of integers with multiplication as binary operation. Okay, so we know that uh, any operation, if we do multiplication with any two integers or any three integers or any four integers, what we will get? We will get integer. Okay, and we know that if we multiply 1 into 2 into 3, what we will get? 6, correct? Then we will get, then if we multiply 3 into 2 into 1, what we will get? 6. So we can say that the multiplication of multiplication of integers are associated. So we have two conditions satisfied, that is closure. First one is closure, and then the second condition is associative law. Now let's check for the identity. Okay, so what will be identity for integers? For integers, identity will be 1, because if you multiply any element with 1, what we will get? We will get the same. We will get the same element. So we can say the identity element is 1 for integers. Now we have to check the, now last condition is remaining. What is that? Is inverse. So if you are going to check the inverse, that for the set of integers, what will be the inverse? No, inverse will not exist. Why? Because we know, because what is the definition inverse? Definition inverse is like that. If 3 is a, then a inverse should be 1 by 3. Why? Because if we multiply the element a by its inverse, we should get the identity, correct? If the element is b, and what will be the inverse? Its inverse will be 1 by 2. Why? Its inverse will be half. Why? Because that will produce 1, that is the identity element. But 1 by 3, what are those? Those are not integers. Those are fractions, right? So fractions do not belong to set of integers. So we can say here the inverse does not exist for the set of elements, set of integers with binary operation as multiplication, right? For set of integers with binary operation multiplication as binary operation, inverse does not exist. Inverse does not exist. So the fourth condition is not satisfied here. Okay, but rest of the three conditions are satisfied. So we can say this is a semi group but not a group, because what is the definition of semi group? If closure and associative law are satisfied, then we can say semi group. So this is semi group, and also we call this monoid. What is monoid? For monoid, all the three conditions are satisfied. Okay, except the inverse one. Rest of all the three conditions are satisfied. So this is semi group. This is monoid. Okay, we can say that. Now, what is finite group and what is infinite group? If in a group G, the underlying set G consists of a finite number of distinct elements, then we say the group is finite. And the order of the finite group is defined as the number of the elements. So if we have a set G 1, 2, 3, then order of the group will be 3, because it has 3 elements. What is infinite group? An infinite group is said to be a group is said to be infinite if the elements are infinite, right? If the number of elements are infinite in a group, then we say that group is infinite group. Okay, and for the finite group, the number of elements are the order of the group, and for infinite group, the order does not exist, because the order, or we can say the order is infinite. For infinite group, we can say the order does not exist either, or the order is infinite. Now there is a now do an example. So that the set of all real numbers except -1 forms a group under binary operation asterisk defined by a asterisk b equal to a plus b plus ab. So what we have given? We have given the a operation b, binary operation b equal to a plus b plus ab, and also it has been told that the set of real numbers except minus 1. So the set we will be considering that will not include minus 1, or we can say that will exclude minus 1. So it is obvious, if minus 1 excluded from this set, then the operation a plus b plus ab should not produce minus 1. Okay, should not produce minus 1, but we have to prove that the operation a plus b plus ab will not produce minus 1 in any ways. How we can prove that? To prove that, we have to consider a plus b plus ab equal to minus 1. Then we will get 1 plus a plus b, 1 plus a into b equal to minus 1 plus a, or we can say 1 plus a into 1 plus b equal to 0, or we can say a equal to minus 1 or b equal to minus 1, which contradicts the definition of S, right? Thus, for any a b belongs to S, a plus b will never be equal to minus 1. Now we have to check the closure. So how can we check the closure? We know that a operation be equal to a plus b plus ab, and we have already seen that it will not never produce minus 1, right? It will never produce minus 1. Hence, S is closed with respect to the binary operation star, right? With respect to the binary operation star, right? Because we have already checked that a plus b plus ab will never be equal to minus 1. So the operation we are doing for a plus b plus ab will never produce minus 1. That means that the operation is closed, because this set, this, I mean, when you checking group, what you will check? You will first check whether this is a binary operation, whether the elements of the set is closed under the binary operation or not. So we can see that yes, the set is closed under the binary operation, because the binary operation will never produce minus 1, which is excluded from the set, correct? So we can see that. So you can say that yes, it is closed, the binary operation is closed here. Now we have to check whether it is associative or not. For that we can write like this: a plus a binary operation b binary operation c. Now we know that b binary operation c equal to what? B binary operation c equal to what? B plus c plus bc, as per the definition of the binary operation. This question often come in university exams, so you can follow that. So a plus b, b plus c plus bc, a into b plus c plus bc. So a plus b plus c, bc plus ab plus ac plus abc, correct? And similarly, if we do a operation b operation c, we will get a plus b plus c, b plus bc plus c plus abc. So we can say that a operation b operation c equal to a operation b operation a into a operation b operation c equal to a operation b operation c, correct? Hence, this is associative. This is associative. Now what will be the identity element here? What will be identity element? 0 will be the identity element here. Let's check that. If we do any binary operation a, any element a with 0, what we will get? As per the definition of binary operation, a plus 0 plus a into 0, a from that what we will get? We will get a plus 0 plus 0, that is a. Then 0 binary operation a, what we will get? 0 into a, 0 plus a plus 0, that is equal to a. So for all a belongs to S, we can say identity exists, and that identity is 0. So we can say the identity is 0 here, right? The identity is 0. Now whether we have to check whether inverse exists or not. So we can assume that the inverse may be multiplicative inverse over here, but we have to check that whether the inverse is really multiplicative inverse or not, or whether the inverse exists or not. Okay, whether the inverse exists or not. So for that, what we can do? we just check with that. We just check with that. Let A dash be A inverse. That A we know that this is A inverse. Just go through my previous video per set. I have just explained. I mean group theory. I explained what is inverse in detail. Okay. So this is A. If A be the element, that then its inverse will be A to the power minus 1, right? Now we know the definition of the binary operation that is given here, that A binary operation be equal to A plus B plus AB. So in that accordance we can write that A in plus A inverse plus A inverse A equal to 0, or we can say that A plus A into 1 plus A inverse equal to 0, that is A inverse equal to minus 1 A by 1 plus minus 1, and we know that A plus 1 is not equal to minus 1. A plus A equal to not equal to minus 1 as per the definition. Then the element minus 1 minus A divided by A plus should be a multiplicative inverse of A, correct? So here inverse also exists. So we can say this the binary operation A binary operation B equal to A plus B plus AB on integers except on, just saw the question for once. Saw the question for once. Real numbers. You can say real numbers. Okay. So you can say the binary operation. What is the binary operation? A binary operation B equal to A plus B plus AB. So we can say the binary operation A binary operation B equal to A plus B plus AB over the real numbers excluding minus 1 forms a group. Rather it forms a abelian group. Why? Because A binary operation B equal to what? A plus B plus AB, that is equal to B plus A plus BA, and that is equal to B a binary operation A. So we can say that this also forms a abelian group. Okay, so the binary operation A binary operation B equal to A plus B plus AB over the set of real numbers excluding minus one not only forms a group but also it forms an abelian group. Okay, this is very important question. It often comes in university exam. So you just go through this example. Okay, if you go through this example, you that will give you clear understanding of group, then abelian group also. This is a very good exercise as far as university examination is concerned. Okay, next, another question. Prove that the fourth roots of unity, that is set of 1 minus 1 I and minus 1, is an abelian group with respect to multiplication as binary operation. So this table is called multiplication table. Okay, so the table is called multiplication of multiplication. So you can show the these are the rows of the table and these are the columns of the table. So in the row, what we can say, this is the operation multiplication. In the first row you see the first row, first column, the multiplication is the operation. The first row, second column, the first element plus 1. First row, second column, we have put the second element minus 1. First row, third column, we put the third element plus I. And the first row, fourth column, we have put minus y, right? Now check. In the second row, we are considering in the first column of the second row, we have put 1, correct? We have put plus 1. Then plus 1 into plus 1, we get 1. Plus 1 into minus 1, we get minus 1. Then plus 1 into plus I, we get I. Then plus 1 into minus I, we get I, correct? In the third row, first column, we put minus y. Then we multiply minus 1 into plus 1. What we will get? Minus 1. Into minus 1 into minus 1. What we will get? Plus 1. Then we multiply minus 1 into plus I. What we will get? Minus n. Then we multiply minus 1 into minus I. What we will get? Plus 1. Right? Similarly, in the fourth row of first column, we put minus 1, minus I. Then we multiply minus y into plus 1. What we will get? Minus I. minus I into minus 1, we will get I. Minus I into plus I, we will get 1, correct? We will get 1. Minus I into minus I, we will get minus 1, correct? Because I square equal to minus 1. We know I square equal to minus 1, correct? Now, now from this table, what we can see that whatever result we getting, all belong to the set of, all belong to this set, all belong to this set. That is the first result. So for the first multiplication result, while what we have get 1 minus 1 I and minus I. So all these four belong to the set. In the second case, what we will get minus 1 I 1 minus I 9. Also all of these four belongs to the set. In the third case with plus I, what we will get I minus 1 and plus 1. That also belongs to the same set. And for minus y, we get minus I plus I 1 and minus 1. That also belongs to the same set. So we can say the set with the binary operation as multiplication is closed. The set with the binary operation as multiplication is closed, correct? Now we check the associativity law. So it associativity follows from the fact that real numbers and complex numbers are associative. I mean, multiplication of real numbers and complex numbers are always associative. Multiplication of real numbers and complex numbers always associative. We can check like this. 1 into minus 1 to minus I equal to 1 into minus 1 into plus I. What we will get? Minus I. Correct? You can check that. You can remember that multiplication of real numbers, and I have written this. Look, take a screenshot of this. Multiplication and real and complex number are always associative. Now, if you want to check, you can check like this. I have checked one. You can check all the elements of this set. You can check with all the elements of this set. Correct? So 1 plus minus 1 into y equal to 1 plus I into minus 1 plus minus 1 into y. Or you can check like this. I into minus I plus 1. What we will get? Minus I into I equal to 1 minus 1. Minus I into I equal to what? Plus 1 into 1. That will be 1, correct? That will be 1. Now I into minus y. Okay, I into minus y plus 1 into 1. What we will get? Again we will get 1, correct? So you can check like this. So what will be the identity of the element? The identity is 1. And this is obvious from the first row of the table. So in the first row of the table, what we saw that we multiply plus 1 into 1, we will get 1. If you multiply plus 1 into minus 1, we will 1. It is obvious that if we multiply any element with 1, we will always get the same element, right? So 1 is the identity here, okay? And the fourth one is inverse, correct? The fourth one is inverse. So we can see that fourth one is inverse, because if you, so for 1, the inverse of 1 minus 1 plus I and minus y are respectively 1 minus 1 I minus I and I. Why? Because 1 into 1, what we will get? 1. Minus 1 into 1, what we will get? 1. Minus I into I, what we will get? 1. Minus I into plus I, what we will get? 1. So these are the inverse. Okay, so these are the inverse. So for plus 1, inverse plus 1, minus 1, inverse minus 1, plus I, inverse minus I. For minus I, inverse is plus I. Correct? Like 1 into 1, we will get 1. Minus 1 into minus 1, we will get 1. Minus I into I, we will get 1. I into minus I, we will get 1. Correct? Hence, we can say the inverse exists. Correct? Inverse also exists. So, and we know that if we multiply 1 into minus 1, what we will get? Minus 1, and then 1 into minus 1, what we will get? 1. So we can see that A binary operation B equal to B binary operation A. So we can say this is abelian group. This is not only group, this is abelian group. How? Look, if we multiply 1 into 1, what we will get? 1. 1 and 1 into minus 1, what will get? Minus 1. Then minus 1 into 1, what will get? Minus 1. I into minus y, what will get? 1. Minus I into I, what will get? 1. Correct? So we can see the binary of the operation A binary operation B equal to B binary operation A. So this is not only a group, this is also abelian group. Correct? Now properties of group: left cancellation and right cancellation hold in a group. Okay, how? Let G is a set with ABC as member and star be a binary operation. Okay, so if A binary operation B then equal to B, A binary operation B equal to A binary operation C, then B equal to C. We have to prove that. How can we prove that? To prove that, you can write like this. We can take inverse. Taking inverse at left side. Taking inverse at left side. A inverse, we have taken A inverse as left side. So A inverse binary operation A operation B equal to A inverse binary operation A binary operation C. Correct? Or you can say A inverse A binary operation B equal to A inverse A binary operation C. That is E binary operation B equal to E binary operation C. At what that produce, that will give us B equal to C. Okay. Now taking the inverse at the right side, what we will get? The same thing we will get. The same thing we will get. Same thing we will get. Correct? So what? So what was the property? Take the screenshot all of this. Take a screenshot of this. It will give you a very good notes of set theory. Left cancellation and right cancellation exist. And how you prove that? This is the proof. Take a screenshot of this. Now in a group, solution of equation exists. How will prove that? Let A binary operation x equal to B and Y binary operation A equal to B. Correct? So A binary operation x equal to B. Okay? So just take inverse. Taking inverse at left side. A binary operation A inverse binary operation A binary operation x equal to A inverse binary operation B. Okay? Okay? This is the thing we have taken. So what we will get? A inverse A binary operation x equal to A binary operation A inverse binary operation B, or identity. This will give us identity. So identity into x equal to A inverse B, or identity to binary operation x will give us x. Correct? And what we will get? X equal to A inverse B. That will give us the equation. That will give us the solution of equation. Correct? So what we considered? A binary operation x equal to B and y binary operation A equal to B. Correct? Now we will proceed with A binary operation x equal to B, and we are proceeding with we will first check with A binary operation x equal to B. For that we have taking the inverse at left side. A inverse. So A inverse A will give us identity that and if we do binary operation with identity with x, we will get x. Correct? And x will be equal to A inverse binary operation B. Correct? A inverse binary operation B. So solution of equation exists here. Solution of equation for y you can also check. For y you can check like this. For y you can check like this. A inverse binary operation y A inverse B, correct? Then we can say A inverse A, then Y equal to A inverse B, correct? A inverse A will give us identity element, Y equal to A inverse B, correct? And identity element of binary operation Y, we will get Y equal to A inverse B, correct? Now, in a group, identity is unique. In a group, identity is unique. How can you prove that? Let E1 and E2 be two identity elements. Okay, then A identity element will E1 will give us A binary operation E1 will give us A, correct? Because if we do binary operation of any element with identity, then we will get the same element. We'll get the same element, and then E2 is another identity. So if we do binary operation A with E2, then again we will get A. And what does that mean? That means A binary operation E1 equal to A binary operation E2, and by the left cancellation we see the left and right cancellation hold for groups. Left cancellation and right cancellation holds for group. In the previous example we saw that, right? So you can say E1 equal to E2. That, what does that mean? That means the identity is unique, that is E1 equal to E2 equal to E, correct? The identity is unique. Now inverse of an element is unique. Here inverse of an element is also unique. How can you prove that? Let inverse of an element be A is A1 inverse and A2 inverse. Okay. Then we can say that as per the definition of inverse, that A binary operation A1 inverse equal to E, and A binary operation A2 inverse equal to also E, correct? This is as per the definition of inverse. Okay. Then we can say that A binary operation A1 inverse equal to A binary operation A2 inverse. Okay, by the left cancellation, what we know, that A1 inverse equal to A2 inverse. This is very easy. That is equal to A inverse. That is inverse is also unique here. These are very very easy examples. I have written this in such a way that you can understand in one shot. You can understand in one shot. So uh, just uh, listen this video. Just watch this video again and again to understand these things. If in one shot you don't understand, don't be hopeless. Watch this video 3, 4, 5, 10 times. You will understand all the things. You will understand the group theory will become very easy topic for you. Okay, I will giving you the question answers which will often come in university exams in my next videos. Okay, but at first, before going to that, you should understand what is group, what is binary structure, what is binary operation, what is subgroup. Okay, what are the properties of group, what is the properties of group. Only then you can understand the question answers, correct? If I just give you the question answers, you may not understand, because you don't know what is binary structure, don't know what is binary operation, you don't know what is group, what is subgroup. If you understand all this, then the things become easier for you. I mean, to understand the question answer, if you want to understand question answer, you have to understand these things first. If you understand these things, then you will understand the question answers in very easily. Okay, it will be very easy for you to understand the question answers. Okay, next, the property. This is also a property. If a b a binary operation b whole to the power inverse a binary operation b, okay, whole to the power inverse equal to b inverse binary operation a inverse. How can you prove that? First take the right handed side. First take the right handed side. First take the right edges. This is the right hand side and it is the left hand side, right? This is the left hand side, this is the right hand side. So first consider the right hand side. Right hand side, we are B inverse, binary operation inverse. We are uh, let's do a binary operation with A, binary operation B. Then what we will get? We'll get, we can write like this: B inverse binary operation A inverse A, binary operation B. Correct? We can write like this. If we just take this B inverse, correct? What we will get? B inverse, we just keeping B inverse outside. We keeping B inverse outside. Then we are doing the binary operation with A inverse. What we will get? We will get A inverse A inverse A. This is A inverse A, then A inverse A inverse A inverse B. We are doing the binary operation with A inverse first. What we will get? A inverse A, binary operation A, binary operation B. Keep the B inverse outside. What we will get? What we know that A inverse A equal to E. That, and if you do that, what we know that A inverse A will give us the identity element, and if we do the binary operation with any element with the identity element, we will get the same element, that is B. Now B inverse is outside, so B inverse binary operation B, we will get the identity element E. Correct? We get the identity element E. Again I am going through. We are, this is the right hand side, B inverse binary operation A inverse. We are doing a binary operation with this, with A, binary operation B. What we will get? First do the binary operation of binary operation with A inverse with A, binary operation B. So what we will get? A inverse A, A inverse binary operation A, binary operation B, and we know that A inverse binary operation A will give us E, that is the identity element, and B is remaining here, and E binary operation B will give us B, and B inverse is outside, and we know that B inverse binary operation B will give us identity element. Correct? So this is what we will get. This we will get identity. Now do the same thing. A binary operation B whole inverse binary operation A, binary operation B. What we will get? E, identity element. Correct? This is the property. This is as per the property of inverse. So we can say LHS equal to RHS. So what we can say, that A binary operation B whole to the power inverse equal to B inverse binary operation B inverse binary operation A inverse, B inverse binary operation A inverse. Okay. Now let G asterisk is a group, then left identity can be right identity. This is another property. Left identity can be right identity. So A binary operation E equal to A. Okay, we can say that, we can write like this: A binary operation E equal to A. That is the, we know that if we do binary operation of any element with the identity element, what we will get? We will get the same element, right? So we have written this, that A binary operation E equal to A. Now taking inverse, okay, we are taking the inverse, so we are taking A inverse. So A inverse A binary operation E equal to, we can write that A inverse binary operation equal to A. Okay, then A inverse A we know E, and E binary operation E will also be E, and A inverse A will give us E, right? So we can say that E equal to E. In a group, left inverse is also right inverse. How can we prove that? We can prove like this: A inverse A, we know E. Then taking A inverse at right side, we know A inverse A inverse C, that is A inverse A binary operation A inverse, that is A inverse binary operation E, that is E binary operation A inverse equal to A inverse binary operation E. Correct? So from there we can see that left inverse is also right inverse. As per the cancellation law, left inverse, that is E binary operation E inverse, will always be equal to A inverse equal to binary operation UAT, that is left inverse and right inverse are the same. Okay, now next question, so that the set of matrix A alpha equal to cos alpha sin alpha minus sin alpha cos alpha, where alpha is a real number, forms a group under the multiplication. Okay, let M denote set of matrix, let M be the set of matrix. Okay, set of matrix, that is cos alpha minus sin alpha and cos alpha, where alpha belongs to real numbers. Okay, alpha belongs to set of real numbers. Okay, it is to prove that M is a group with respect to matrix multiplication. Okay, so we'll first check the closure properties. So let A alpha and A beta belongs to R, A alpha and A beta belongs to R, where alpha beta belongs to set of real numbers. Okay, then we have A alpha multiplication A beta, that is the matrix multiplication. So the matrix as per the matrix multiplication we will get this result. As per the matrix multiplication we get this result. In the previous video I have already told you that if you don't have idea of set, relation, then function and matrix, you may not understand abstract algebra. Okay, so if you are not understanding this, please go through the matrix, go through the video for the matrix. Okay, and then you will understand how matrix multiplication happens. Okay, here I cannot make you understand that how matrix multiplication is done, because I am imparting you training on group theory, not in matrix multiplication. If you want me to upload the notes about matrix, please comment. I will upload the notes of matrix, because I have already uploaded the notes for set theory, notes for functions, notes for relations. Okay, so if you want me to upload notes for matrix, just comment that please upload the notes for matrix. I will give you the note for matrix. Okay. Okay, so as per matrix multiplication we will get this. Just take a screenshot of this, and I think you can search Google for matrix multiplication to understand how multiplication happens. Okay, and then and as per this we will get cos alpha plus beta minus sin alpha plus beta, then sin alpha plus beta, and this cos alpha plus beta. Okay, so that, what is that? That is A alpha plus beta. Since alpha plus beta belongs to R, so A alpha plus beta belongs to M. So closure is satisfied here. Now by the properties of matrix multiplication, that is why I am telling you that go through the matrix, because the matrix multiplication is always associative. As per the property of matrix multiplication is always associative. Okay, so second condition is also satisfied. Now the existence of identity. So if we consider A0, then we will get cos 0 minus sin 0, sin 0 and cos 0. Okay, that is A0 multiplication A alpha equal to A0 plus alpha, because A alpha, A beta equal to A alpha plus beta. We have seen that. You know that A alpha into A beta equal to A alpha plus beta. So if you do A0 multiplication alpha, then what we will get? We will get A0 plus alpha, correct? A0 plus alpha, that will give us A alpha, right? So A0 is the identity here. Now check the existence of inverse. Let A alpha belongs to M, then A minus alpha belongs to M. Therefore minus alpha belongs to R. Okay. Now A minus alpha into A alpha equal to A minus alpha plus plus alpha, because we know A alpha, because we have already seen that A alpha into A beta equal to A alpha plus beta, correct? So that will give us A0. So the left inverse, this is the left inverse. Similarly, A alpha into A minus alpha will get A alpha plus minus alpha, that is E0. That is the right inverse. Okay, so we can say that A alpha into A minus alpha equal to A alpha plus A minus alpha equal to E0. So A minus alpha is the inverse of A alpha. Okay, hence M is group under matrix multiplication, right? Correct. So M is group under matrix multiplication. So what we learned today? We learned today what is binary structure, what is binary operation, what is binary structure, what is group, what is abelian group, what are the properties of group, and then some examples. Okay, then some examples. So please consider this video as a very good note for abstract algebra groups. Groups belongs to abstract algebra, correct? So consider this video as a very good note for abstract algebra or group theory. Okay, so whatever example you have given, whatever you have seen, just take a screenshot of this. I'm going through from the beginning once, so that you can take the screenshot one by one and take a printout of those and pin up those. It will become a very good note for the group theory. It will be very good for you to understand. It will be very easy to understand group theory. Once go through this, just if you have go through this video for once, twice or thrice, and if you look at your textbooks, okay, you will understand group very easily. You will understand group theory. If you initially look at your books, it may seems like this is a very complex thing. Group theory is a very complex thing. Okay, but if you just go through the video for once, if you go through the video for once, twice or thrice, and then you just look at your textbooks, you will find that no, group theory is not a complex one. It's a very easy thing. It's a very easy thing which is very easy to understand. Okay, so go through the video for once, twice, and thrice. Okay, and then you go through your textbooks. You will find group theory very easy. You will find group theory. Even all the questions, all the examples that you have that has been given in your textbooks as far as the university exam is concerned, you can understand those very easily. In my next video, I will give you I will make you understand what is permutation group. Okay, what is called cyclic group. Okay, what is permutation group, what is cyclic group. Then I will implementing a subgroup is very important as far as university exam is concerned, because there are several, there often questions comes from subgroup. Most of the question as far as group theory is concerned, most of the questions comes from subgroup. As far as group theory is concerned, most of the questions comes from the subgroup section. Most of the question comes for this subgroup section. But if you don't understand what is group, then you may not understand subgroup. Yes, from the group portion also, there at least you get as 16 or 20 number questions. Okay, at least 10 to 20 marks will come from group theory, and you can consider 20 marks from subgroup. I mean, group in a section. I mean, when you the as far as the abstract algebra paper is concerned, you will have in your first semester, you will have group theory and ring theory basically. Okay, so 50 marks you can consider from group and 50 marks from ring. Okay, so in these 50 marks from groups, you can consider 20 question will come from group theory. I mean directly from groups, and 30 from subgroups. Okay, 30 from subgroups. So both are very important here, groups and subgroups. But because as I told you that sometimes 30 comes from subgroup and 20 comes from group, and sometimes 30 comes from group and 20 comes from subgroup. Okay, so you have to learn both of these two things precisely. Okay, you have to learn both of these two things precisely. And for that, whatever I have given you, you have to go through it before consulting your textbooks. Go through this video for once or twice or thrice, and then consult your textbooks. You will find the group theory very easy. You will find very easy. You will group theory very easy, and you can secure all the 50 marks.